To understand intelligence, we must stop seeing biology as magic and start looking at it as mechanical hardware. Take the human eye. To pull an image into focus, the eye has to physically change the curvature of its lens. This difficult mechanical feat requires the tissue to warp precisely, bundling incoming light rays into a single sharp spot on the retina. This diagram outlines the problem. On the left is the human eye, warping its lens. On the right, human engineers solve this in a camera by taking a fixed, rigid lens and sliding it back and forth. Biology knows how to do this too. Fish evolved rigid lenses that move forward and backward to focus, just like engineered cameras. So why does the human eye rely on a much harder, less efficient mechanical solution? We tend to assume biological systems are perfect from scratch designs, but the eye proves they are anything but. Evolution cannot start with a blank piece of paper. It is entirely constrained by the physical materials and blueprints left behind by previous generations. Biologists call this the path of gradual change. Every new biological feature has to be built as a tiny, survivable modification to an existing structure. It is the equivalent of trying to rebuild a bridge across a canyon while the traffic never stops flowing. This limitation fueled a long-standing debate among scientists, famously documented by evolutionary biologist Richard Dawkins. Skeptics argued that intricate structures possess irreducible complexity, the idea that they are far too precise to evolve through small random steps. Current scientific consensus tells us that is false. There is no irreducible complexity in biology. We have overwhelming evidence that these structures are simply the sum of endless, tiny compromises made over millions of years. The human eye exists as a living fossil, carrying the developmental baggage of the ancestors that preceded it. This brings us to a persistent debate in neuroscience and artificial intelligence. If the eye is weighed down by its history, what about the brain? Many robotics engineers and computer scientists rely on a top-down shortcut. They assume that if we can just map the final wiring of the brain circuits, we can reverse engineer true intelligence. The logic goes like this. The brain is just hardware. Therefore, the messy metabolic processes, the hormones and the chemical states, are just biological noise we can afford to ignore. Historically, this approach has worked. We have built highly successful mathematical models of artificial neurons without simulating a single real-world molecule or biological chemical. But this relies on the assumption that the final, visible blueprint is the only factor that dictates how the system actually works. Developmental biologists push back on this hardware shortcut. They argue that circuits carry the historical burden of development. When scientists map out actual biological brains, they frequently find connections and architectural features that make absolutely no sense from an engineering perspective. They look like dead ends or wasted energy. These connections are artifacts of how the biological network physically grew from a single cell, scaffolding that remained functional during construction. You cannot delete these awkward connections in simulation. The brain's current functionality, routing electrical signals, relies heavily on pathways built by messy growth. If you strip away the history of how the circuit was built and simulate only the logical parts, the simulation fails to capture the properties of the whole brain. Intelligence isn't a final destination you can teleport to. You cannot reverse engineer a brain without accounting for the inefficient journey that built it, which forces us to ask, are digital artificial neural networks free from this baggage? They are built from clean code, not messy cells. The programming of an AI isn't written all at once. It happens through training, one data point at a time, creating developmental growth. Biology and AI are both bound by a concept called algorithmic unfolding. Here is how this looks. A network state, let's call it state T, dictates exactly how it processes the next input to become state T+1. Feeding the exact same data in a different chronological order builds a structurally different network. For an artificial neural network, the specific sequence of its past experiences, its memory, literally becomes its physical architecture. The quirks of the human eye, the tangled growth of brain tissue, and the digital code of AI all share the exact same limitation. There are no shortcuts to mapping intelligence. You cannot untangle how a system functions today from how it developed yesterday. Whether you are trying to understand human consciousness or build the first true digital life form, the rule remains the same. You are your history.